morning, good afternoon, everyone. I guess we have friends from all over the world. Welcome to this youth talk session. I hope you can hear me loud and clear. Um, Firstly, I will just give a brief introduction to myself. My name is Sheng. I'm currently an associate professor in the School of Mechanical and Manufacturing Engineering at University of New South Wales. And also I'm an associate professor in the School of Electronic Computer Science at the University of Southampton. So I will be the moderator for this youth talk session. So I won't take much spotlight and think the most important thing is to introduce our speakers and panelists today. And of course, we need to introduce the topics of today's session. Today, we want to give a overview of recent advances in liquid metal enabled chemical, mechanical, and electronic technologies. So we have three speakers today. It's an great honor for me have this opportunity to host this session. Thanks, Alice. Thanks, ICAX, to enable this all these things to happen. And we have three speakers. The first speaker is Dr. Sheng from Shenzhen University. The second speaker is Dr. Rahim from Monash University, Australia. And the last speaker is Dr. Kelly from Queen Mary University, London. And we have two panelists today. The first panelist is Dr. Meng Wang from Central South University, China. And our second panelist is Dr. Shu Jian from Harvard. So the first speaker is Dr. Yan Shen from Shenzhen University. He's currently an assistant professor, and he received his PhD from the University of Wollongong in Australia in 2017. And from 2018 to 2020, he conducted his postdoctoral training at Hong Kong University of Science and Technology and the University of Tokyo. He has published more than 80 high-impact journals. His research interests include microfluidic biosensors and biodevices, as well as liquid metal-enabled soft electronics. Dr. Yan is the recipient of numerous prestigious fellowships, such as the Australian Endeavour Research Fellowship and the JSPS Fellowship. So now let's welcome Dr. Yan to share his insights in liquid metal microfluidics. So Dr. Yan, please feel free to start sharing your screen. Thank you. I will stop sharing.
Yeah. Can you hear me? Yeah.
Yes, I can hear you.
Yeah. Okay. So let's get started. Thanks, Professor, kind introduction. I'm Sheng Yan from Shenzhen University. My personal background is mechanical engineering. So my research is try to apply liquid metal in mechanical engineering. So today's research topic is liquid metal enabled soft microfluidics. So let's get started. In nature, there are a variety of objects we are human beings. We are at meter scale, and our hands are tens of centimeters, and the diameter over here is about 100 microns, and the size of the momentum cell is about tens of microns. And there are some smaller objects in nature, like protein virus. They are at a nanoscale. Our hands is quite flexible. We can use our hand to pick a hair, but it's impossible to use our hand to pick a single cell, right? So this is impossible, and that's why we need the microfluidics. Actually, microfluidics tool can handle objects in microscale. Actually, microfluidics has applied for various biological applications like organ chip. We can culture the organ on the chip, which have the great potential to replace the animal model for the drug screening, and also it can conduct single cell analysis because this is impossible in the conventional biological lab, because in the biological lab we can only use a pipette to pick the cell, but with microfluidics we can capture one only single we can capture one cell and conduct single cell analysis, and also we can use microfluidics to control the cell, so the cells can focus into a single line, and they can pass through uh, the imaging area and can take very nice images. So this is called the imaging flow cytometry, that we can obtain the morphology of the cells, and also we can combine the microfluidics with the optical sensing or electrical biosensing for the point of care testing. Here, this is the method we fabricate the microfluidics. This is the glass microfluidics. This is the first generation of microfluidics. Actually, we use wet etching and hot temperature bonding to seal the microfluidics. Yeah, this is the first generation, and this is second generation of microfluidics. We generate the channel on the plastics and use the high temperature bonding to put two layers of the plastic together. So this is to seal the microfluidic channel. And this is the second this is second generation of microfluidics. Actually, this is very commonly used in our lab. Here we use the photolithography and the soft lithography to fabricate the PLMS microfluidics, and then we use the chemical bonding to seal the microfluidics. From this, you can see all the devices are rigid. So once they fabricate it, they can't be changed any longer. So that's the limitation of the rigid microfluidics, because we use the hard substrate and they have the fixed geometry. When they fabricate it, they can be only used for very specific applications. So that's why we need the but nowadays we have the new demandings, like we hope the microfluidics can be variable, flexible, or tunable. So that's why we need the soft microfluidics. Actually, soft microfluidics is flexible and variable, can attach our scan, and also we can modulate the channel geometry by rolling it or stretching it. So now we have two questions. The first question is how to fabricate the soft microfluidics, and what are the new applications enabled by the soft microfluidics. So in this talk, I will try to answer these two questions from two aspects. The first is the fabrication, another is application. Uh, yeah, I will explain this one by one. First of all, we build the liquid metal mold. First of all, we use the leather to cut the patterns on the adhesive sheet and attach it to the Cooper surface, and then we drop the liquid metal on the surface. So here they are liquid, so they can spread out on the Cooper surface, and also they have their metals. The liquid metal can amalgamate with the Cooper, so that we can generate the very stable liquid metal mold. And here we use the electrochemical method to manipulate the liquid metal. And after we generate the liquid metal mold, we pull the PLMS or the soft elastomer, and after peeling it off, we have the microfluidic channel. Here you can see we can control the channel profile just by changing the liquid metal volume, and also we can control the channel width to get the different profiles of the channel. And here we can control the patterns of the liquid metal mold. This is the letters UW, because when I did this work, I was at University Wollongong. So this letter is for Universal Wollongong, and we can generate the Christmas tree and the spiral channel, spanning channel. This are very typical microfluidic channel for the cell manipulation. And here we can here I want to mention that uh, we can generate a channel with a different head and different widths. This is impossible with the photolithography, because using photolithography, we can generate the channel with very uniform channel the channel has the uniform head. So with the uh, 3D microfluidic channel, we can use it for the fluid mixing. This is the microfluidic channel generated by the conventional photolithography. Here you can see this is plenary channel, and the two incoming flow, they won't mix into the channel because of laminar flow. But in our 3D microfluidic channel, you can see two coming liquids are mixed very quickly due to the uh, secondary flow generated at the cross section. And yeah, we can also use the liquid metal mode to generate the PMS DOM array, and then we can put another layer of liquid metal composite. Here, this is the way we prepare the liquid metal composite. We mix the PMS on powder liquid metal and mix them together, so to prepare the pressure sensor. And we can monitor the movement of the human beings. And this work has been selected covered by the advanced material interfaces. Previously, we can use the liquid metal mode to generate the microfluidic channel, and later we scaled down the channel width, and we found that when we peeled it off, we can get the complete electrical circuit on the elastomer. And my students investigate the fundamental behind. We found the hydrogen bond and the Young's uh, surface tension contribute to this phenomenon. So that's why we can, when we uh, peel the elastomer off from the liquid metal mode, and we can have the complete electric circuits on this elastomer. So that's the soft electronic circuit. And we apply it for uh electro electrothermochromic sensor. Here we mix the thermochromic ink into the EcoFlex, and here you can see with the different strain, uh, we have the different color, because this the color is the indicator. And also this sensor can identify the location of the pressure. And you can see with the different touch, we can have the different color use our sensor. And also it can be used as the electrochemical sensor. Here we use our liquid metal as the electrodes. And so due to the substrate is Ecofast, which have the which is flexible. So no matter you twist it or you bend it, the signal the electrochemical signal is stable. Previously, you can see we can generate the soft microfluidics, but all the devices is based on the Cooper surface. So to solve this problem, we generate the liquid metal mode Bohr 2.0. So this is so update our fabrication method. So you can see, first of all, we generate the Gantt wire, and then we reconstruct the Gantt wire into the freestanding structure, and then we use the elastomer to encapsulate the Gantt wire, and then we remove the Gantt after heating. So this is the um, uh, freestanding channel, 3D channel. Here we have the three approaches to fabricate the freestanding liquid metal mold. The first one is the 3D welding assembly. We put the Gantt wire together, and at the low temperature welding, we can have such kind of 3D molds. And also we can use the bender to generate such kind of spiral structure, and we can also combine this method together. And now we have the freestanding liquid metal mold, and actually this liquid metal mold is compatible with many elastomers like PMS, EcoFlex, and modified PMS. Here you can see EcoFlex has first have the strong capability in have the strong stretchability, so we can use the EcoFlex uh, to generate such kind of 3D structure, or we can elongate the the EcoFlex channel, and then we can modulate the channel geometry. And also this modified PMS is self-adhesive, so that it can attach on scan and have the and you can see they can deform with our body movement. So what are the new applications enabled by the microfluidics? Here, so based on my expertise, I found two applications. For the first one is the tunable self-separation. The second is the wearable plus multi-bar sensors. So for the cell separation, I have conducted this. I have worked in this area for many years from my PhD study. In the past years, I have conducted the plasma separation, micro LED separation, ETH separation, planet classification, cancer cell classification. So you can see all these devices are rigid. So every device is designed for the specific application. For example, if this channel is designed for the micro LG separation, it can be used for the E separation because the size of the E cell and the alga cell is different. To solve this problem, my research group developed the ultra-stable microfluidic channel. So you can see this microfluidic channel is made of the EcoFlex. So we mount the EcoFlex channel on the stretching stage, and if we stretch the channel, you can see the geometry or the channel the channel diameter will be changed. So the cell movement will be changed as well. Here we use the viscoelastic or non-Newtonian fluid for the cell separation. Then for the new non-Newtonian fluid, you can see in everyday life like honey or blood, they are non-Newtonian fluid, and here we use a PO polymer to prepare the particle suspension, and actually this is the shear-thinning fluid. Here, this is the fabrication process of the ultra-stretchable microfluidic channel. Just like it is just like I just mentioned before. So here we use the EcoFlex, and the EcoFlex has the strong stretchability than the PMS, the stretch ratio can reach up to over 500 percent, and you can see and also the EcoFlex also has the similar transparency with the PMS, and this is you can see if we elongate the channel and the channel diameter will be changed as well. So this is the particle moment in the ultrasound channel. So we use the microparticles to test our channel. So with the different, you can see for the between micron particles, they they won't focus in the microwave channel. But with 100% channel elongation, the particles focus in the microwave channel due to the viscoelastic effect. And also this phenomenon happened for the 10 micron particles, and also you can see for the a small particle like 5 micron particles, they won't mix under the channel elongation of 100%, but with the increase of channel elongation, we can see the particles can focus in the center line of the channel. So the particle moment can be modulated by our ultrastructural channel. And here we introduce the shift flow into our channel, and here the particle will be introduced from the side inlets, and the particles will be confined at the side walls of the channel. And for the large particles, they can migrate to the centimeter, so they will exit from the middle outlet. For the smaller particles, they will be collected from the side outlet. Here you can see with the different strand, we can collect the different cells. Here we make a summary. For example, without channel elongation, all the particles will pass through from the side outlet. With 100 channel elongation, we can collect the large cell from the middle outlet, and we can collect the rest cell from the side outlet. Here, this is the separation threshold that can be tunable just by stretching of a channel. You can see with a different strand, the separation threshold can be modulated. And actually, this is the first time for us to propose the ultrastructural microfluidics, because we also compare with the existing technology. Most of them use the PMS. For the PMS devices, the stretch ratio is about 100%, but for the ultrastructural microfluidics, the stretch ratio can reach up to 500%. And this work has been selected and covered art by the analytical chemistry. The next application is the viral plasmonic biosensors. Here we use the surface enhanced Raman scattering for the measurement. Previously, we can generate the search hotspot on the Kuiper tab, on Kuiper particles, or we can use the dilateral phases to manipulate the silver nanowire, and then we can assemble the search hotspots between microelectrodes. Recently we also can generate the search hotspot on the silicon. So you can see after the search measurement, this particle will removed. So the next fresh silica will come into this detection area. So we call this mobile search hotspots. And these devices have been used for measure the biological and the chemical moleculars. But all these devices are rigid; they can't be wearable. So recently my research group developed the wearable microfluidics. So with erasable liquid metal plasmonic hotspots. Here, uh, this is the microfluidic channel. Uh, this is made from the PI pyramids. Actually, we add the PIE pyramid to increase the adhesion of the pyramid, so they can attach to our scan. And also, inside microwave channel, there are gallium droplet here, and we can generate the silver nanoparticles on the surface of the gallium droplet. And also, we decorate the silver nanoparticles so that they can capture the glucose molecular in the sweat. So you can see the sweat can come into the channel, and the glucose will be selectively captured by the thirst hotspots. So we can measure we can do the thirst measurement and measure the concentration of glucose in sweat. And also we can after the thirst measurement, we can add the sodium oxide and to remove the silver nanoparticles. So that's we call this the erasable liquid metal plasmonic hotspots. Here you can see the limit of detection is very low. It's about the limit of detection is about 1 nanogram per liter, and it can be used for several times. And also, this is all volunteer, and we can measure the uh, glucose concentration before meal and after meal. So, and actually, yeah, and also this work has also been selected and covered by ACS Applied Materials and Interfaces. So yeah, let's make a summary. Uh, uh, Now previously, we can generate the liquid metal mode at micro scale, right? Uh, and we can use our liquid metal mode to generate the soft microfluidics, and we applied for the tunable cell separation, and it can also be we can also turn the microfluidic into the viral microfluidics for the spread detection. Yeah, in the future, we would like to develop the liquid metal mode at another scale, use some advanced fabrication technology like high resolution laser, e-beam lithography, or 3D printer, and to build the more advanced microfluidic channel, so it can be used for the some exome separation or bacterial separation. We try to separate some objects in at nanoscale, and also it can be used for the biomarker detection. So lastly, I would like to thank for my supervisor and my collaborators, and here this all my excellent students. Without them help, I can't make so much progress. And thanks for the funding agency. All right, thank you. Yeah.
All right. Thank you so much, Dr. Yan, for wonderful talk. We're going to leave the Q&A session in the end. So yeah, thank you so much. And probably you can stop sharing. I will introduce the next speaker. Okay. All right. So yeah, we are absolutely on time. So our next speaker is Dr. Arifur Rahim. He is currently a senior lecturer at the Department of Chemical and Biological Engineering at Monash University, Australia. He obtained his PhD from the University of Melbourne. And following his PhD, he continued as a postdoctoral fellow in the same group and later moved to UNSW Sydney to investigate the chemistry of liquid metals. He was the recipient of the Australian Research Council DACRA Fellowship. And excitingly, this morning, ERC just announced that Dr. Rahim has been awarded the prestigious ERC Future Fellowship. So big congratulations. By far, Dr. Rahim has published more than 70 papers, and many of them are in top journals such as Nature Chemistry. I think that's it for a brief introduction. Now let's welcome Dr. Rahim to share his excellent work in liquid metal catalysts. So it's all yours now, Dr. Rahim.
Right. Thank you. Thank you very much, Sheng. I'm going to share my slide now. Yeah. Is it good enough?
Yeah, it's good. Loud and clear. Thanks.
Yeah, thank you very much, Xiang, for the nice introduction, and really happy to see the award being the fellowship being announced today. So I'm in a good mood to talk. So let's say that. So as Xiang introduced, my name is Arifur Rahim. I'm a senior lecturer and an ARC Future Fellow. It was just ARC DECRA Fellow just before this meeting. So I have changed it. And I'm from the Department of Chemical and Biological Engineering at Monash University. And today I'm going to talk about the single atom catalyst, dynamic single atom catalyst, which is liquid in nature. But maybe I will just start with a little bit of the themes that I work, which are one part of it is not directly related to liquid metal, but a few other parts are pretty much related. So let me just go through just to have an idea of my the extent of my research expertise. Okay, something like really sorry, like everything's stopped. Okay. All right. I don't know why it is responding then. All right. So I basically started my career when I was in PhD with the coordination chemistry of natural polyphenols. And liquid metal or liquid gallium for that matter, it was not completely unknown to me, but I was more like interested in the coordination chemistry. So all the speakers here are pretty much aware of the chemistry of liquid gallium. So everybody knows that we mostly work on the neutral form or the metallic form of gallium. We do have problems with the gallium oxide, which we will tell a little bit later. This coordination chemistry, and I was really aware of the gallium chemistry in the segment where people looked at the iron catechol chemistry. And it's been a long time that people knew the antibacterial effect. And gallium, I knew gallium that time, that gallium can be a bad receptor for many of the bacteria. One of the reasons for this is that iron and gallium is pretty similar in ionic radius. But unlike iron, gallium doesn't go with the redox cycle as iron does. So iron gets 3 plus to 2 plus, and this cycle bacteria uses for their own production and their life cycle going. So gallium doesn't do that, and many of the time, if they take gallium by mistake, gallium ions here, by mistake, they get killed. So that is where the antibacterial effect of gallium is coming, but nowadays there are some alternative explanations too. Anyway, one of the polyphenol chemistry that I have been doing in the beginning, it's for coatings. And when I started looking at the liquid metal in 2019 at UNSW Sydney, it was quite a straightforward choice for me. Up until then, the surface active agents were quite limited. And I thought that, okay, this coordination chemistry I can use that I learned from natural polyphenols. And I will show you in the next slide maybe some of this earlier work. Then while working on this, I started to develop some of the composite materials with polyphenols and liquid metals. And then I also got interested in the catalysis area of liquid metals, which would be covering most of the talks today. So some of the works that we have done, these are some of the achievements here on the bottom, and hopefully many more to come in all these three themes that my group is working. So I think all the speakers are pretty well aware. I'm just giving a little bit of overview of liquid metal. On the left, these are some of these metals that we call in general liquid metals. And one of the salient feature is that their melting point is low. And of course, when you say liquid metal, the first metal that comes in our head is possibly mercury. There has a lot been done in 50s and 60s on mercury. Then this their hazardous impact comes into play, and we are left with only one option. I would say a few more, but only one option, and mostly gallium because it's liquid near room temperature or around 30 degrees centigrade. So liquid metal is fascinating. They have plenty of properties, stimuli responsive. And I think that what is shown here, this is just a tip of the iceberg. There may be a lot of surprises waiting for us. And I'm really glad that I can contribute to some extent and like to explore this area as much as possible. So these are few of the areas that we mostly work in liquid metals. So as a reaction media, we do work, use their metallic properties like the electrical conductivity for soft electronics. And catalysis, I think this is the most hot area, at least for me. And of course, composites, I will tell you some of the areas that we can still explore. So these are some of the examples, early examples when I started working. You can see on the left, this is the very first project I remember. And it was basically one of my one of the project that I delivered during my at the start of my DECRA. So what I realized is that this surface active agent or lowering the surface tension of liquid metal is important for soft electronics or e-skin kind of applications. And I initially realized going through the literature that it is the regular surfactant has been in use and they have limitations. Now, natural polyphenol, you can see a structure on the left. This is called tannic acid. This has been used for centuries. Even in your writing ink, if you can remember, we used to have an ink that we can write down. It's like a black color. These are basically tannin, iron tannin complex, which is quite impure, but you can get a pretty pure compound nowadays. So the main component of tannin is tannic acid. So tannic acid, one important connection between tannic acid is that another big field, bio-inspired field, possibly you are pretty well aware of, is muscle-inspired chemistry, which essentially deals with the catechol chemistry. And this tannic acid has got a lot of this catechol group that can attach to any surface. So the idea was that can we modify the liquid metal particles with this sort of surface active agent which contains catechol, and we can use that adhesion or adhesive properties of the polyphenolic structure to make them write on any surface. And this is exactly what we did. We prepared an ink using liquid metal and tannic acid, and we were able to write by a ball pen that you can see on the bottom and on the left hand side. So we were able to write them, and if I can remember correctly, we were able to write on 28 different substrates. So that's like quite a huge range, and that coming from the surface active agent as catechol containing tannic acid that have on the surface of liquid metal that lowers the surface tension, that can wet any surface and can adhere to any surface. So that was quite a remarkable work. I think one of the latest work that we have done. This is also on a composite. So what we tried to do is that a solar thermoelectric generator that we published last year, and it is something to do with the coordination complexes of natural polyphenol with other metal ions that can have a ligand to metal charge transfer band, which is basically, you see, what does it mean is that you see sometimes, depending on what metal you are using, depending on that, it can show visible color. So for example, with iron, the tannic acid will become pretty black, bluish. And if you are using titanium iron, for example, titanium 4+ iron, then it would look orange reddish. So the idea was that, so it is light absorbing in the visible range. And the idea was that can we use this absorption and also use the liquid metals metallic conductivity to create a system which can possibly give you a solar thermoelectric generator under solar irradiation. And interestingly enough, in this paper, we showed that our system was so good. You can see on the right side, and you can see that when it is under light, the thermal property, the temperature goes up really, really quickly and goes up to almost like 60 degrees in about 30-40 seconds. So that was really a good composite. And we, in fact, made a record, this 345.5 that I show on the right-hand side. It's possibly twice or thrice than any other solar thermal generator solar thermal electric generator at that point of time. So it was quite good. We are still exploring this area of solar energy harvesting, but not in a manner of solar cells. So these are some of the areas that we are exploring along with the catalysis field. So this is kind of like the key findings of that paper, that the design and other things, if we think smartly enough, there is a lot can be done in the composite area too. Okay, so let's come to the real one. So we, from the beginning of my journey in liquid metal from 2019, we have been looking into liquid metal catalyst. So this is one of the very early example that one of my colleague published this, and we were trying to get some CO2 reduced and form carbon flakes or something like this in with some silver nanoparticles. So that was the journey. We published a few papers. These are just pure gallium droplet with some silver particles as well. However, working in this area, I started to realize something. So I'm going to share some of my personal insights here, just to give a broader perspective to the viewers. So one of the aspect that I realized is that many of the current researchers coming from different backgrounds in liquid metal chemistry, and the people who has been developing this field, this is not new. Many of the phase diagrams that you see with liquid gallium, that dates back to 1950s or even earlier. And many of them has been done in Russia. So one of the Russia, Japan. So one of the things I started realizing is that when you see a phase diagram, you always see that there is a liquid region, there is a solid liquid region, then there is a solid phase formation, and all these phases are there. But one interesting part is that when we talk about the solubility, up until that time, it was not taken seriously what exactly meant by solubility. To me, coming from a chemistry research background, although I'm a chemical engineer by training, but from this chemistry knowledge of this, something is soluble to me is like you put a sodium chloride in water, you disintegrated every piece of sodium and chlorine, and they gets into as a sodium ion and chlorine ion in the system. Now, if you apply that same analogy for liquid metal, and if you say that something is soluble in there, to me, it's already in that solubility limit. They are atomically dispersed. So that was one of the key idea that we basically generated. And this is a list that I looked at. This is one of my good friend, Torben. He published this fantastic review paper. I think this is really, really good. If I need any information or background check, I always look at this paper and go through it. And this table is just phenomenal. It's a nice compilation of all the works, and you can see that one of the fascinating property of gallium is that it can be used as a solvent, and it can, depending on what metal you're using, it can essentially dissolve a range of metal. In fact, almost like 80% or 90% of the metals in the periodic table. So it really caught my eye that even if these solubility parameters and other things that come into play, and their temperature range is higher, but it was up until that time that nobody thought that even if the solubility is low, and if the other metal is catalytically active, can we use them? Or so it was the beginning of the idea, and I think that this field of atomic dispersion and liquid-like atoms in a gallium matrix, this field is really, really flourishing. We have been publishing heavily, but I think the combination and permutation is just massive, that we don't know what to expect next, but that is the fun side of it. All right, so just to give you an idea about the solid state catalyst, because we always have to compare the solid state single atom catalyst, because this is also not a mature field yet. Still, people are exploring this. And this one, so theoretically, everybody knows that we start with bulk metal, of course. 100 years back, we used to have the catalyst in bulk state. Then we realized that we are just misusing most of the atoms, and we come to nanoparticle. Then we are in the area of single atom. Now, one of the problem with single atom catalyst in the solid state is that they have metal matrix interactions, which essentially doesn't give you a theoretical limit of the catalytic activity of a single atom, because your matrix interferes with them. And honestly speaking, I still don't see, even in my comprehension, that how this can be done. I mean, I can think of that putting an atom in vacuum and check any reaction in there. But in vacuum, you can't run any reaction. So basically, what a single atom's catalytic activity, we would possibly never know. But we can get closer to that. And possibly the only one way to go is possibly using a liquid metal matrix. Anyway, so here are some of the examples of the solid state catalyst. There are very few of the ones are, I think the very first one was in 2011. Then some of these come into play, the using different kind of 2D metrics, and then putting the different catalytic, non-catalytic atoms in there. Around that time also, we have few publications where people use molten metals, not really gallium, but bismuth or that sort of things. But the reaction or the model reactions that have been looked at, these are at a very high temperature. One reason I can think of is that many people thought that, okay, at high temperature, when you have an alloy, they are molten, then we can do the reaction, and we have to select the reaction in that way because your solubility of both of them are pretty high. So these are few of the examples here, but up until 2022, we didn't have a system which you can use at relatively low temperature. So here comes one of our work in 2020, where we call this liquid platinum. So what we did basically is pretty straightforward. Have solid platinum with a known amount, dissolve them in liquid gallium, but the solubility limit is really, really low, but still they will dissolve quite a lot. But I must say that they're low, meaning that it goes to 0.001 atomic percent. But we didn't know that, since we didn't know what is the highest level of a single atom's catalytic activity, maybe that is enough. And that is how I perceived this work. And it was really, really fascinating journey. This work was for me. And one of the things, I think one of the characterization that we have done by simulation, that kind of like a format now that people look at, we do some experimental characterization like XPS, XRD. You can basically check whether the dispersion of this metal that you are dissolving, the solid metal, whether they are atomically dispersed. And of course, we have to maintain the solubility limit at a specific temperature. And then we have the simulation that confirms all these results. We do some more. But what was really fascinating, initially, I was not believing either. So these are very few of the model reactions that I checked with this liquid platinum. And like, this is fascinating enough that most of cases, like we tried oxidation and reduction reactions, then enzymatic and some electrochemical reactions. And what is fascinating, that the activity, the platinum specific activity that we get, despite that the platinum solubility in gallium at 50 degree or 60 degree was really, really low, still the platinum specific activity that we were getting is 3 to 5 orders of magnitude higher than any existing catalyst, including the single atom solid catalyst. So 3 to 5 orders magnitude is just massive. It appeared to me that it can solve the real problems of our life. Anyway, that was a start for this sort of works. We are so what we learned, because we looked at most of the fundamentals, and what we learned really is that the atomic dispersion and liquid light dynamicity, that plays a huge role in getting these kinetics going up that much. Then we also noted that the activation of surrounding gallium atoms, that they get activated along with the active metal that you are doing, and they show some unique electronic characteristics that I'm not going to go through into details. You can get a pretty good picture if you go through the paper. All right, so how do we expand this field? This is quite a big field, catalyst. So this is kind of like a like my own thinking that how we should go about it. So of course, we call it the liquid catalyst, dynamic liquid catalyst. We can either go on the bottom, or go on the top, or can do both. So we have to understand more. We do not know many things, so fundamentals. Then can we rationally design something? Then we have to look at the metal matrix interactions in a more careful way, that what we are seeing is real. Then in terms of exploring different kind of reactions, or different applications, let's say, because every reaction comes with some sort of applications. These are the three bottom ones that you can look at: redox and enzymatic reactions. In fact, my feature fellowships, I'm going to look at these enzymatic reactions in more detail. Then organic and fine chemical synthesis, and remember that all these reactions can be done at a relatively low temperature. All right, so this is one of the work that currently undergoing. What we are looking at is a liquid palladium. So we looked at liquid platinum, and the reason for choosing liquid palladium is that we are basically looking at the Suzuki-Miura cross-coupling reaction. And these results looks fantastic up until now. I'm not discussing this slide that much. This is pretty much the similar behavior that we have seen in platinum and palladium work. So palladium within the solubility limit, again, it's pretty good. Their electronegativity difference is pretty similar to platinum as well. So along with gallium, you will see the similar electronic impact. The only thing is that palladium has been known for Suzuki-Miura cross-coupling. Here are some of these examples of conversion and thing. The most important thing is here. So in this table, we basically came up with the turnover frequency of this system. And I have red highlighted the TOF for this system, which is almost 10 to the power 7 times. So 7 order of magnitude higher than any existing palladium catalyst. So this is huge. So we are looking forward to this, and I believe pretty much that not only this single solid in gallium matrix, but maybe many more. We'll talk about a couple of few surprises, I think, in next few slides. One of my colleague and friend, he has been exploring some of the high entropy systems and make some nanoparticles, and looked at some of these reactions. It's been recently published in small structures. So these are I call myself, this is a multi-element system. So you can either choose to see the impact of these elements, that what really happens in a liquid state when they're high entropy. Liquid state, they're already in a high entropy state, but when you have multiple elements, then what really started to do. So this area needs to be explored way more than this one, but we just started looking into this sort of systems as well. So this is, as I said, that liquid metals can provide you surprises, and this is one of them. We published this paper last year, and possibly you have seen this. We looked at two metals dissolved in gallium, nickel and tin, in gallium, and we wanted to get some oil like a long hydrocarbon chain and look to see that what they produce or whether they can be catalyzed. It's a very straightforward system. You mix them, heat up to 200 or something, look at the hydrocarbon, that's its vapor pressure, its vapor range, that when it starts to vaporize, if you're within that limit, that's fascinating. Now, one of the surprising thing that we found was that when we added these two metal, there is a configurational match, because we looked at a range of different hydrocarbons, and every time we found out that we are producing propylene. So this catalyst was chopping off the hydrocarbon chain, or this whole chain, in a very specific manner, which you can't even think of that the way enzyme works. So that's very, very specific way that enzyme works, that doesn't let other things to enter in a pocket. It's something like this, that the metal produces a very interesting configuration, and that matches with the configuration of the reactant that you're using. So that was really, really fascinating, and the precise alignment of the metal atoms to the reactant, that was one of the key findings of this one. So I will finish up. I think I'm pretty, I'm like a minute or something over. So I like to thank Sheng Yu. Thank you very much for inviting me here. Australian Research Council, my students and colleagues from University of Sydney, Monash, and UNSW as well, and my collaborators from quite a lot of places in Australia, UNSW, RMIT, Deakin. Then we have some active collaboration at New Zealand and from US as well. Thank you very much.
Thank you, Dr. Rahim, for such a wonderful, like a beautiful insight of a liquid metal catalyst. So once again, we're going to leave the Q&A session till the end. Since previous two speakers talked about mechanical, chemical properties of liquid metal, our next speaker is going to talk about the electrical aspect of liquid metal. Our next speaker, probably let me share my screen again. Sorry. Okay. Cool. Okay. So our next speaker is Dr. James Kelly. Dr. Kelly is currently a senior lecturer in the School of Electronic Engineering and Computer Science at the Queen Mary University of London in the UK. Dr. Kelly received his PhD in microwave filters from Loughborough University in the UK. And after his PhD, he worked as a postdoc at different universities like Loughborough, Birmingham, Sheffield, and Durham. And Dr. Kelly has extensive industrial experience. He has worked for a few renowned companies such as Interfleet Technology, Rolls-Royce Strategic Research Center, Airbus Defense and Space, and European Aeronautic Defense and Space Company. And in 2012, he decided to return to academia and became a lecturer at Anglia, Ruskin University, and the University of Surrey. In 2018, he joined Queen Mary. By far, Dr. Kelly has published over 150 papers. So I understand that Dr. Kelly is still on his annual leave, so I really appreciate he can allocate some time to join us today. So now let's welcome Dr. Kelly to share his works in liquid metal enabled circuits and antennas. Thank you. I'll just hand it over to you now.
Thanks a lot, Sheng. Yeah, so let me share my screen. So can you see my slides now?
Yes, I can see a slide here loud and clear.
Marvelous, thanks. So yeah, my perspective on liquid metal, as Sheng was saying, is a little bit different from the others. And what I'm going to focus on is the high frequency electronic aspect of liquid metal. And we'll talk about how we can use liquid metal in reconfigurable high frequency circuits. So this is an overview of the things that I'll discuss in this presentation. And I want to start, because I know we've got a multidisciplinary audience today, I want to start with a few primers, just introducing a few concepts that you might not be familiar with. Then I'll give an introduction to the work that I'm going to show, and then get on to going into showing you some devices built using liquid metal. So let's start with the primers. The first thing I want to say, based on the title of the talk, is what do I mean by high frequency? Well, I'm talking about sinusoidal waveforms like this at frequencies above about 300 megahertz. Above about that frequency, then we talk about RF, radio frequency, and microwaves. Next question is, what do I mean by an antenna? Well, I think we've all seen antennas. This is an example of an antenna. It's a satellite TV reception antenna, but you might not be exactly familiar with what antennas really do. Well, their job is to capture and transmit radio waves from and to the air. I'm going to talk to you about beam steerable and beam switchable antennas later on in this presentation. So I want to talk through a few terms that we use in connection with those kind of antennas. This little schematic is showing a kind of beam steerable antenna known as a phased array antenna. You might have heard of that before. But these concepts relate to all beam steerable and beam switchable antennas. Anyway, from that kind of antenna, we can generate a number of beams, and I'm showing these beams schematically with these dashed lobes. So we can steer the beam in different directions. We use a term called directivity, or sometimes we talk about gain, and that relates to the sharpness of this beam. In other words, how narrow that beam is. And that's a really important concept for antenna engineers. Another important concept is the steering range. So that's the total angular range over which I can steer my beam. Another really important concept for antenna engineers is scan loss. So that first of all, we need to think this antenna by default generates a beam in a certain direction. For this particular antenna, that nominal direction is zenith, straight up, in other words. And if you look at what happens as we start to steer the beam outwards, the amplitude of the beam drops down, and we refer to that as scan loss. It's undesirable. The final thing that I want to mention is steering resolution, and that is the minimum angular step through which I can steer or switch my beam. Okay, so all of that will be used later on, but let's just pause that for a minute and go into the introduction. So this whole talk is about reconfigurable high-frequency circuits and antennas. Well, what do I mean by reconfigurable? Well, first, let's talk about the conventional scenario. We're probably all familiar with some high-frequency systems. I showed you one, satellite TV reception. Of course, another one is cellular phones that we all have. they're both examples of high frequency systems, but the antennas and circuits inside those kind of systems are typically fixed in their performance at the time of manufacture. But if we could reconfigure the performance of those components, then the system would be capable of responding to changes, for example, in user needs or in the operating environment. So actually, this reconfigurable capability is really potentially very valuable. Okay, so now let's talk about how we might go about achieving that kind of reconfiguration. Well, like most topics in research, there's been lots of work done on this over a long period of time, and there's lots and lots of different methods that have been put forward. And I'm not going to give a comprehensive review of all those methods, but I'm going to mention a couple of the most popular ones, and those are to use semiconductor-based switches and tuning devices, or to use mechanical movement. But both of those popular techniques have some serious limitations. Semiconductor switching and tuning devices that's a very mature technology, and these things are commercially available. However, there's some important limitations. The devices themselves have a complex input impedance, which makes designing with them quite complicated. Because if I want to use that switch or tuning device at a different frequency, I have to consider its reactive behavior and what it looks like at that different frequency. So it's quite complicated to design with these things. Another problem is we have power dissipation inside those devices, which means from an antenna engineer point of view, I get less energy out of my antenna because some of that energy is dissipated in the semiconductor. Another problem is that there's a limited tuning range due by when we use those kind of devices. And the last problem that I'm going to mention today is poor linearity, which means to say if I put a complex signal through that antenna that incorporates a semiconductor, what comes out is a distorted version of the signal I put in. Now, I'm not going to go into that in detail, but you can perhaps imagine that when we want to communicate, distortion of the signal that I'm trying to transmit is bad news. Now let's look at mechanical movement. We can do great things with mechanical movement. I can, for example, make an antenna with 0 scan loss, but as with all things in engineering, there are pros and there are cons. And some of the disadvantages are that as soon as we introduce mechanical moving parts, we need to have a periodic regime of maintenance, repair, and replacement. So I've added to the running cost of the system. So in very general terms, what are the alternatives to these two approaches? Well, in very general terms, one alternative is to alter the bulk property of materials, and gallium-based liquid metal is one such a technique. Because basically with gallium-based liquid metal, I can add and remove whole regions of metal from my antenna. Effectively, I can redraw my antenna on the fly. A lot of the other presenters have talked about the properties of gallium-based liquid metal, so I'll only just sketch through some of these points. Gallium-based liquid metal isn't the only metal that's liquid at room temperature. There's mercury, there's cesium, there's rubidium, But those other alternatives have some serious limitations. Mercury is toxic. Cesium and rubidium react violently with water. So gallium is fairly attractive as an alternative. There are some commercially available alloys of gallium, such as E-gain and gallinstan, and we used E-gain throughout all of our work. The electrical conductivity of gallinstan and E-gain is pretty high. And if we talk about E-gain, the conductivity is around about 17 times lower than that of copper. I mention copper because copper is the main metal that we use in antenna engineering. Okay, like all of the other work presented today, this is highly interdisciplinary work. It involves manufacturing. We need to consider manufacturing, for example, manufacturing fluidic channels, such as by 3D printing, or apparatus to move the liquid metal around. We also need some awareness of mechanical engineering, such as awareness of the fluid dynamics of liquid metal, and awareness of chemistry, such as the reactions between liquid metal and copper. And the last speaker was talking about some of those reactions. So let's step into the research itself now. Firstly, I want to talk about some research that we've done over a period of quite a few years on frequency and bandwidth reconfigurable antennas for this CR stands for cognitive radio. Okay, so this is a very, very busy slide. This picture, I don't expect you to pick up on all the details in this. This is a picture of the frequency allocation table for the UK. In other words, what's being shown here is how the radio frequency spectrum between 300 megahertz and 30 gigahertz is divided up and shared between different users. And what I want you to appreciate from this busy picture is that it's a very complicated and busy spectrum. And you might assume from a picture like that the spectrum is fully utilized and, in fact, overcrowded. Well, that's true in part. Some areas of the spectrum are overcrowded. But if we were to look at the spectrum at different times in the day, we would find actually that some bits of the spectrum aren't being used. They're allocated to a certain user, but that user isn't using that spectrum all of the time. And that's where this concept of cognitive radio came about, because people were thinking, well, if this is the case, could we have a radio that was a bit smarter than the current radios? Could we have a radio that would listen to the spectrum, find a free slot, and operate in that free slot? And that's where we come to reconfigurable antennas, because to do that, some people were saying you need a wideband antenna to do the listening, and you need an agile narrowband antenna to move to the available spectrum and start communicating. And over a period of several years, we developed lots of different antennas that could do that kind of thing in different ways. And the bottom set of pictures show some antennas that can change their operating bandwidth. So, for example, they can switch between wideband and narrowband operation, or they can switch between different widebands. And they all did that by changing where the ground plane of the antenna appears to be. So let's take this antenna as an example. This antenna is quite simple in its concept. It's a type of antenna known as, well, in one of its modes of operation, it's a type of antenna known as a microstrip patch antenna. So here we've got a ground plane, and above that we've got some bits of metal. If we connect those isolated bits of metal to the ground plane, then we have a conventional microstrip patch antenna, which radiates over a narrow range of frequencies. And you can see its operating performance in grey here. If, on the other hand, I disconnect all these isolated bits of ground plane from this main ground plane, then what I've essentially created is a wideband antenna. This is a classical wideband antenna known as a monopole, and its performance is shown in black. And when we did this initially, we did the disconnection using silicon-based switches, okay, which have all the disadvantages I spoke about earlier. Also, we're only making the connections at discrete points. So later on, it occurred to me, well, what if we could just redraw this metallization, essentially? And of course, with gallium-based liquid metal, we can do just that. So we revisited this work, and we added gallium-based liquid metal into some channels here to essentially redraw those connections. So here you see a PDMS channel which is not filled, and when it's not filled, we get this black performance here, which is the ultra wideband mode, which is actually better in performance than we got when we were using the switches. And when we add the liquid metal, we get the blue curve, which again is better than what we were getting using the switches. We get better performance, we get better radiation patterns, we get less distortion. I mean, these patterns are pretty much what you'd expect for a patch antenna, and the efficiency is very high. And these are the patterns for the ultra wideband mode. Okay, so that's some work that we were doing on bandwidth reconfiguration. Now I want to switch on to a different topic, and this is low loss beam switching and beam steering. Remember, I talked to you about some concepts in relation to that earlier. But why did we want to look at beam steering and beam switching? Well, you're probably aware of 5G and 6G needing or potentially needing in the future beam steerable antennas for millimeter wave communication. But the current generation of millimeter wave phase shifters, which is a component that you'd need to make a phased array antenna, are very, very lossy indeed. Also, we've got scan loss, which I mentioned to you earlier. That's a kind of a power loss. So we've got two important sources of power loss that would really hamper the operation of millimeter wave antennas. So we set about trying to develop some switches and phase shifters that were really, really low loss. And we based those switches and phase shifters on waveguide, a special kind of waveguides called substrate integrated waveguide. And it's based on this rectangular waveguide that you see here. Imagine I had a section of rectangular waveguide, and I can pass microwave energy down this waveguide. But as soon as I put this blocking wall in here, imagine I put a blocking wall in here of metal, then I stop the passage of microwave energy from one end of the waveguide to another. And imagine that I could add or remove that blocking wall dynamically, then I've got a kind of a switch, okay? Now, this is a kind of a waveguide that's formed in a printed circuit board fashion. And the side walls of the waveguide are formed from these wires, and the top and bottom walls are formed from metal. Okay, now again, imagine that I have some wires here, and I can imagine I can add and remove these metal wires. These create walls that I can add and remove to allow or stop the passage of microwave energy through this structure. So I've created a kind of a switch here. And this is a practical realization of that switch that we made. It works at fairly low frequencies, around about 3 gigahertz. And here you can see the transmission performance of that switch. So it's very low loss. That's the main message here. And when the switch is in the off state, very little energy goes through the switch, and that's what this picture is showing. Use that same kind of blocking wall technique to create a phase shifter here. And what you can see is we've got 1, 2, 3, 4, 5 walls that we can add and remove. Based on the configuration of the walls, we can send the microwave energy in different directions. And this is a picture of the microwaves going through the structure. And by routing the microwaves through different paths, we can change the electrical length of the path that they go through and change the phase shift. We also added some small wires here to add extra phase shift. So we can create a wide range of different phase shifts. Again, it's very, very low loss performance. Here's a different phase shifter that works at 10 gigahertz. It's using those small wires to incrementally change the phase shift. And you get these relatively small increments of phase shift, all the way from 0 to 360 degrees of phase shift by turning on different numbers of these wires, which are turned on by adding or removing liquid metal into holes here. Again, it's very, very low loss performance. Then what we did is we used 4 of those kind of phase shifters along with 4 antenna elements to create a phased array antenna. And we can steer the beam of that phased array antenna between plus and minus 38 degrees with a scan loss of just 1.5 dB, which is pretty low for that range of beam steering. Okay, now in the last few minutes, I want to go on to some more exotic steering techniques that we developed and that are possible using liquid metal. So here I'm showing schematically a picture of an antenna. It's a microstrip antenna. It's got a radiator in the middle, and it's got 3 sections of ground plane beneath it. The middle section of ground plane is always there, and the 2 edge sections can be added or removed. So when all the ground planes are in place, the beam is directed towards zenith. If I remove this ground plane here, then the beam steers towards that removed piece of ground plane, or switches towards that removed piece of ground plane. Similarly, if I remove the other ground plane, it switches in the other direction. And also, my radiator in our practical antenna was a little bit more complicated. It has some parasitics to enhance the gain, and also enable us to do some additional beam switching, because we switched those parasitics on and off. Okay, so this is the complete practical antenna. We were using some fluidic channels to create ground planes 1 and 3. Those are the removable ground planes, remember. And we use those switchable wires that you've seen before to switch the parasitics. So, and also in addition, by changing the amount of liquid metal in these ground plane channels. We could achieve continuous steering of the beam, not just discrete switching. So in fact, the switchable antenna can achieve these 4 different angles, but the continuous steerable can achieve any angle. Okay, and we got quite good performance, 9 dBs of gain, and a scan angle range of plus or minus 30 with about 2 dBs of scan loss. That's quite good steering performance. I want to talk about 2 more exotic antennas for beam steering. This is an interesting concept where we sort of had one antenna hidden inside another. Now, here's a picture of the fabricated prototype. We had some parts of the antenna that were solid metal, and some parts that were removable. So the removable parts are the parts shown in yellow and green. So when we have this configuration, we have the so-called bullseye antenna. And that is created when we fill these channels with liquid metal and we remove the green channel. Then we get a boresight beam and we get 13.9 dBs of gain. Okay, if on the other hand, we remove all the the liquid metal from all the yellow channels, we add the liquid metal to this green channel, we create a Yagi-Uda antenna, which creates a beam at 76 degrees. So we've switched the beam from 0 degrees right out to 76 degrees with just 2 dBs of scan loss, 2.5 dBs of scan loss. Here's my final exotic antenna that I want to show you today. This was created by a kind of a waveguide radiator with a slot that's radiating upwards. Then we have a number of reflectors, and these various channels are 3D printed, and we can fill one of the channels to create a reflector that then directs our beam in a certain direction. So let's take 2 examples. I've got 5 different channels. Let's imagine I fill the channel at minus 20 degrees relative to the normal. Then I get a beam that's directed 6 degrees, and I get 15.9 dBs of gain. If on the other hand, I fill this 60-degree channel, then I steer my beam right out from nearly 0 to 97 degrees, and I've lost in the process only 3 dBs of gain. So that's a massive steering range and quite a low scan loss. So what I want to sort of say in summary is we can do some quite radical things with liquid metal at high frequencies and achieve quite low loss. Okay, so I'd like to thank Sheng for inviting me to talk today, and I'd also like to thank the PhD researchers and postdoc researchers whose work I've shown today. These are the references which, if you're interested, I can send you offline. And thanks a lot for the time.
Thank you, Dr. Kelly, for such a comprehensive introduction to your reconfigurable circuit antenna. Before we enter the Q&A session, let me start introducing the 2 panelists. Please allow me to share the screen. Dr. Kelly, yes, cool.
Yeah, sorry.
No problem. All right. So we have 2 panelists today. The first is Dr. Meng Wang. She's currently an associate professor at Central South University, China. She obtained her PhD in 2017 at the North Carolina State University in the USA, focusing on electrically controlled liquid metal reconfigurable antennas and microwave devices. So I think her direction matches with Dr. Kelly's direction perfectly. After PhD, she joined Central South University, and Dr. Wang currently current research is mainly focused on reconfigurable and flexible antennas, and also machine learning enabled fine tuning of antenna and microwave devices. So by far, she has published more than 40 journal papers in journals and as well as in conferences. So our second panelist is Dr. Jian Shu. He is currently a postdoc researcher at the School of Engineering and Applied Sciences at Harvard University. He obtained his PhD not so long ago, in 2022, from the University of Science and Technology of China. His research focused on soft actuators, liquid metal, enabled, for example, artificial muscles and bioprinting. He has won several awards, including the Chinese Academy of Science President's Scholarship Special Prize and the Chinese Academy of Science Outstanding Doctoral Dissertation Award. Dr. Shu has published more than 15 papers in international journals and conferences. Firstly, I would like to thank all of you to participate in this youth session. I really appreciate your wonderful talks, and I think now I have to ask you to turn your mic, probably all of you. Let me see. All right. Do I have to stop sharing to make sure everyone's profile photos is on the screen? I'm not 100% sure. Okay. Just give me a second. All right. I just can see my own profile photo. Oh, okay, great. Now I can see everyone. Fantastic, thank you. So firstly, I will ask Dr. Shu to kick-start the Q&A session. I'll ask a few critical questions. Doesn't have to be extremely critical, but so that's my role. I'll be the moderator. So thank you, everyone. Dr. Shu, you can start your question.
Okay, thank you, Sheng, for the introduction. I have to say it's my great honor to join the ICANX talk, and it's my first time to be here. Thank you, ICANX talk, and thank you all for the inspiring talks, and I learned a lot. So the first question to Dr. Yan, I kind of like the work you use use gallium to fabricate microfluidic channels. So what do you think about the biggest advantage of gallium compared to other modeling materials, like some materials whose geometry can be precisely controlled by a 3D printer like that? Yeah, that's my question.
Okay. Thanks. Thanks, Jian. Here, as I mentioned, that here we use the liquid metal because they have they're liquid, so they have the high surface tension. So you can see the profile is very smooth. Although we can use the 3D printer to generate the microfluidic channels, but the 3D printer, the principle of the 3D printer, they generate the structure layer by layer, so it's impossible to generate very smooth surface of the channel. So that's the advantage of the microfluidic of the liquid metal. Yeah, and also the liquid metal they have the phase change. For example, I can I can turn them into solid at the low temperature, and after I encapsulate them, and I can turn them into the liquid, and so they can be washed from the microfluidic channel. So in this way, we can get very complete microfluidic channel without any damage. So, but previously, I see some work they use the fiber to fabricate channel, so they extract physically extract the fiber from the microfluidic channel. So this will cause the damage to the channel. So I think that's I think the two advantages of the liquid metal, one is they have this high surface tension, and also they are fast change material. Yeah, thanks.
Okay, you answered my question. Thank you.
Thank you.
Okay. I'm not an expert in chemistry, but I'm kind of interested in catalysis. I have to say that using liquid gallium work at the solvent is brilliant. So my first question to Rehan is, how do you fabricate such catalytic systems? How do you dissolve metal material like platinum into liquid gallium? Yeah, that's my first question.
Thanks, Jan. Thanks. So the dissolution process, or the making the alloy, is pretty straightforward. So what you do is that generally when I work, I do have a bit of idea on the solubility. So then I decide that how much I will be using my starting material, that the solute I will be using. Then we go slightly higher temperature for 2-3 hours. For example, if it is platinum or palladium. And I would also require a knowledge that at what temperature that I will be using my alloy at the end. So what reaction? For example, I provided an example on the Suzuki Mira cross coupling. So this can be done up until 70 degree, beyond 70 degree, because it uses ethanol as a solvent and a mixture of a few other things. So which is not good. So it shouldn't get. So at 70 degree, so what we do is that we dissolve palladium and have an initial idea from the solubility parameter that, okay, this much amount I would be expecting to be dissolved. Then what we do is that we take big ingots of palladium, or you can use wire or anything, but they have to be pretty pure. Then we just heat it up slightly, not slightly above. We generally heat up just to be sure that they're well dissolved, let's say at 350 to 400 degrees centigrade. Then we equilibrate at the temperature that we want the reaction to run. And generally, it's a pretty big amount that we initially prepare. It's a stock. Then when it equilibrates, we take a very small volume from the top of this stock so that we know that this is the dissolved equilibrated amount at that particular temperature that we.
So the eventually form a kind of alloys, right?
Yes.
Okay.
But these are atomically dispersed alloy because we are within the solubility limit.
Okay. My second question is the oxide layer you mentioned is sometimes alloying in some scenarios when we use it. It's incredibly easy to form even in the air or in water. So does the oxide layer affect the catalytic performance in your work?
Thanks, Jen. I didn't have time to talk about this. I think one of the most problematic aspect of scaling up liquid metal based catalyst would be this oxide layer formation. But I would also say that if you choose your reaction condition pretty carefully, for example, many of the reactions you can perform either at lower pH let's say 2 to 3 or even less, then the oxide formation is pretty limited. Or if it is highly basic, then the oxide formation is pretty limited. And also, if you can carefully use organic solvent. So you are right that we are still kind of like out of the biological rim, just because of the oxide formation. But there are few papers that also coming in, and we need to still look that whether let's say the gallium is kind of like inactive, let's say, which is not absolutely true, but it's just as a matrix, liquid matrix. But there are a few papers coming in that there is a tendency of the solid metal atom that come and can penetrate a little bit that oxide layer if it is thin enough. But honestly, we do not know up until now, but there are many reactions that you can set these conditions in a way that you can avoid the oxidation.
Okay. The last question. Actually, that's not an question. That's just an idea that's inspired by your work. Liquid metal has excellent conductivity, so it's not difficult to induce eddy current inside of the liquid metal when we use magnetic fields. So how do you think about using this kind of eddy current to improve or affect the catalytic performance? Do you think is it possible?
Yeah, Jian, thanks a lot. In fact, this is certainly possible. So if you look at one of our previous few papers, so it really came about like one of the reviewers' questions that we kind of like addressing. That time, this one came about that just platinum specific activity, what we exactly meant by liquid and dynamic. Yeah, so the atoms are dynamic, and we had a calculation that if you think about a chemical reaction, there is a concentration curve that goes like this at the point of a catalyst site. Now, interestingly enough, if you look at this sort of system, what's really happening is that you see a platinum on this spot, then in a nanosecond, or in fact, it's a continuous process. It is not here anymore. It can go here or it can go down. And we had a calculation that almost like per second, each platinum atom in gallium was changing their positions 10 to the power 7 times, possibly, or close to that. Now, the point is that this has a serious impact on your kinetics, because every time your concentration gets changed because you are creating almost like a new position. So it is not precise calculation, but just an estimate. So imagine that you have an eddy current and start to get that diffusion property, start to impact the diffusion property of the dissolved solid, that definitely should have a higher.
Okay. Thank you for your answer. Thank you.
Thank you.
So if Dr. Xu doesn't have more questions, I think now it's for Dr. Wang to raise the questions. Sorry, I think I'm not able to hear you. If it's just my problem.
I think,
No.
Meng,
We can't hear either.
Oh, okay. I think probably Dr. Wang didn't turn on the mic. No, we still cannot hear you.
Oh, can you hear me now?
Yeah.
Oh, yeah, I can hear you now. Great.
Oh,
Yes.
okay. Sorry, I just used my earphones. Actually, thank you very much. Thank you, Sheng and the speakers. And these are very fascinating talk and also very beautiful slides. Actually, as you just introduced, my PhD thesis is about it's electrowetting electron metal based reconfigurable devices and antennas. Actually, my research topic is very similar to Dr. Kelly's topic, but today I still learned and record my experience about the work on the fabrication and especially liquid mold, liquid metal work. So actually now I have two questions for Dr. Kelly. As you introduced, and your group has many work on the liquid metal reconfigurable devices and antennas, and you have very excellent examples of the design. So my question is, first question is about what do you think the very practical limitations if you apply the liquid metal devices, antennas, such phase shifters in a very practical or very real applications, no matter what kind of scenarios. So what are the limitations, like control the fabrication or any other terms? And the second question is that I see you use liquid metal as a wise of the SRW. And so this question is about does the diameter of the liquid metal wise or the channel width, channel height affect your performance of SIW? It's more like a sensitive analysis of your fabrication or size of the liquid metal channels influence on your device performance. So these are the two questions about the limitation and the analysis.
Yeah, thanks a lot for those questions. I think these are very good questions and very important questions. I mean, my own personal opinion is that from an RF perspective, liquid metal works really well and shows great performance.
Yes.
But the practical side of how to use it is more where the challenges lie. So I think your question gets to the nub of something important. So in my opinion, some of the problems of how to use it are how to move the liquid metal around in a way that is competitive with semiconductors, how to stop it sticking to the inside of the channels, which kind of comes back to the first point. And then I guess related is the speed at which you can do that. So I would say these are probably some of the key practical aspects. I mean, I'd be interested to hear your own perspective on that with all your experience in that area.
Yes, I have similar experience about this practical limitation of liquid metal in the real applications.
Yeah. So then coming to your second question about what is the effect of the size of the vias on those structures. I mean, let's talk about the switches that I showed. The size of the vias in the switches determines the extent of the blocking when you turn the vias on. The bigger the vias, the more the blocking. So I could have fewer vias but bigger ones, and I would get the same amount of blocking, if you know what I mean. So that's with the switch, and I suppose that's fairly, obvious that might be the case. With the phase shifters, where we're using the vias for reactive loading, the position of the vias from the side walls of the SIW determines the extent of the phase shift that we get. So if we move the vias closer to the middle, we get more phase shift when we turn each via on. But for a fixed position of the via, if we make the via larger, we get the same effect. In other words, we get more phase shift when we turn that via on. But the negative side of that is, whilst we get more phase shift from that particular via, we also get more reflection from it as well. So so there's a kind of a delicate balance that if we make very large vias, then we can get a lot of reflection, and our reflection performance is quite poor. So you have to be a little bit balance these things out.
Okay. Okay, thank you, Dr. Kelly.
Thanks.
Dr. Xu, I think if you have any more questions.
I have one more question. Just following the Dr. Wang's question, I may have a further question for you, James. Actually, have you noticed the oxide layer on the negative? Maybe it may generate the negative effect on the antennas. For example, have you tested your devices for a longer time? For example, you leave that for 1 week or 1 month, and then you do the test. Does they have the similar or have the same performance? Yeah, that's my question. Yeah.
Generally, yeah. Well, first of all, as to have we done it or not? Yes, we've done it. And then as to whether it has an effect or not, generally we found not.
Okay.
But there was one case where we found it did have an effect, and I'm struggling to remember the details of that one now. But generally, it doesn't have much effect. I think that's partly because the oxide layer is very, very thin. You know, so it's much thinner than the skin depth at most frequencies. So I think it doesn't tend to have a big effect, but where it does have an effect is on these practical aspects like moving the metal around.
Fair enough, because the milliwave or microwave, the wavelength is much larger than the thickness of the oxide layer. Yeah, that's a good reason. Thank you.
Thanks.
We probably have one more question.
I have another question for Professor Yan.
Yeah.
I'm kind of curious about the mechanism behind the glucose sensor. So how do you use liquid metal to detect the glucose in sweat? And do we need to take it off from the skin to detect the glucose?
Here, I will explain this in detail. First of all, we do not use the liquid metal to directly to measure the glucose. Actually, we generate or we synthesize the silver nanoparticles on the surface of the gallium droplet, and then actually the silver nanoparticles can capture the glucose. Then we can we can do the source measurement, and so we attach our devices on their scan, and after sports or exercise, the our sweat go into the microfluidic channel, and then we can do the source measurement in sweat. So that's our devices works.
So the silver nanoparticle is coated in on the surface of liquid metal droplet, right?
You can see that coated, or we can. It's just a replacement reaction. So that's a very simple chemical reaction. So we can synthesize the silver nanoparticles on the surface. Yeah.
Okay, thank you.
All right, so I would like to thank all the speakers and all the panelists for the wonderful conversation. And sorry, I have to share my screen again. second. So thank you everyone. Because you're not physically here, so we cannot